Good morning. So we're talking about the magnetic field of a long straight wire. We don't have to worry too much about how long it is. So we don't whether it's infinitely long, or a mile long, or 10 feet long. If we're near the wire and we're not near the ends, then it might as well be infinitely long. So we've done things like this before, so we're not worried about where the ends are. And we know we've found that the magnetic field rotates around that wire in the sense of the right-hand rule. So if I put my thumb in the direction of the current, and my right hand, my fingers then rotate around the wire, the magnetic field goes around the wire everywhere. So it's got a magnetic field that looks sort of like that. We also know that at a distance, a perpendicular distance of r away, that the magnetic field at that point is equal to mu naught I over 2 pi r. We found that using the Biot-Savart law. That's a general result for a long straight wire. We're going to use that a lot without having to re-derive it every time. We will derive that in a different way later when we learn Ampere's law. But anyway, so we now know a little bit about how wires create magnetic fields. So now let's talk about the force between wires, the force between two long straight wires. So what happens if I put a second wire at a distance from, oops, what happened? If I put a second wire at a distance d, so two parallel wires at a distance d. Let's say that wire 1, we'll just call the top one wire 1, we'll say that carries current I1 up and to the right, and wire 2 carries current I2 up and to the right. And I want to know, what is the force between these two wires? In reality, we're really, once we figure out the force, we'll see that there's a length in there. And what we really mean is, unless I tell you what is the force between 1 meter length of these two wires, or 10 centimeters length between these two wires, we can find the force per unit length. So really, I want to know what is the force per unit length of these wires. So how do we find that? How will we find that? It might seem out of the blue, but remember we had already found the force on a long straight wire. The magnetic force on a long straight wire was IL cross B, right? That was the magnetic. We did a bunch of examples with that, and now instead of just saying the wire is in some arbitrary magnetic field, the force that is on one of these wires is due to the magnetic field of the other one. So here's a situation where we're talking about the force between something, and you got to know what that means, right? It means when we ask what's the force of charge 1, what's the force between two charges, we mean what's the force of charge 1 on charge 2, or the force of charge 2 on charge 1. Those two forces are equal and opposite. Same thing here. What's the force of wire 1 on wire 2, and what's the force of wire 2 on wire 1? Those two are going to be equal and opposite. And we will be able to see that by solving the equation F equals IL cross B, by saying that one wire, right, one of the wires is in the magnetic field of the other wire. And then if we switch the two, we'll find that the magnetic force is equal and opposite. Okay, so let's go ahead and find. So we've used this equation before for a wire in a constant magnetic field. In this case, the magnetic field is not constant in space, but by putting the wires parallel to each other, the magnetic field along one wire due to the other wire is constant, because magnetic field depends only on, of a long straight wire, depends only on the distance r. And so if they're parallel, the distance r is constant. And so it is constant along the wire. So we can apply this equation. By asking what is the magnetic force per unit length between the wires, we're asking really what is the magnetic force per unit length on each wire. So we're gonna do that by first calculating the magnetic field of each wire at the location of the other wire, right? So let's calculate the magnetic field of wire 1 at the location of wire 2. So B1 at 2. right? I'll just write that out so that we hopefully understand what that means. The magnetic field of wire 1 is mu 0 I1 over 2 pi r. But in this case, r is just d, right? So d is the distance from wire 1 to wire 2. So the magnetic field of wire 1 at wire 2 is that. So go ahead and tell me then, what is the magnetic field of wire 2 at the location of wire 1? Oh, oops. I didn't give you a direction. Is it, I'm going to write both, in or out? Is it in or out? Sorry, it's going back to wire 1, the magnetic field of wire 1 at the location of wire 2. Is it into or out of the page? Think about it, right? Do the right-hand rule, and it is into the page. So there's your vector, mu 0 I1 over 2 pi d into the page. Wire 2. What is the magnetic field of wire 2 at wire 1? Well, the magnetic field of wire 2 in general is mu 0 I2 over 2 pi r, where r is d, right? The distance d. We're asking what is the magnetic field of wire 2 at a distance d from the wire. And what's the direction of that magnetic field? Put your thumb in the direction of I2. Your fingers at I1 come out of the page, so that is out. So there's your two magnetic fields. So now let's figure out what is the force of wire 1 on wire 2. The force of wire 1 on wire 2 is I1, right? It's the current, hold on. Okay, so I just made a error, which is very illustrative. We want to know what the force of wire 1 on wire 2 is. So we want to know what the force is on wire 2 in the magnetic field of wire 1. And when we're talking about IL cross B, we're talking about IL cross B, we're talking about the force on a wire in a magnetic field. So let me rewrite that. The force on wire 2 in magnetic field B. So we've got I2L cross B1. That's the force of wire 1 on 2, because we're talking about the force on a current I2 in a magnetic field B1. Okay, so that's in magnitude. It's going to be ILB sine theta, and in direction it's going to be L cross B. Let's go ahead, and L is the direction of the current. Let's go ahead and just figure out what the direction is. So I2 is pointing in that direction, and B1 at I2, we already showed is into the page. So this is B1. And so when we cross, L is the direction of I2. When we cross I2 into B, we find that the force, right, use your right-hand rule, and that sound was me actually doing the right-hand rule, boom, that's me rotating my hand. So when I2, fingers in the direction of I2, boom, into B1, which is into the page, your thumb points sort of up and to the left, perpendicular in that direction. So the force of 1 on 2 is in that direction. The force of 1 on 2, that just says force of 1 on 2, is in that direction. It's an attractive force. That's what that means, right? That I1 attracts I2 magnetically. Okay, so that's toward. We'll just call that toward, or attractive. It's in the direction shown. Okay, so what is so now given the picture, theta is the angle between L and B. So theta is 90 degrees, right? B is into the page, I2 is in the page, so this theta is 90 degrees. And then B is the magnetic field B1, so that's mu 0 I1 over 2 pi d. L is not given, right, because we're actually doing force per unit length. And I is I2. We had not put those subscripts, I2, B1. So therefore, we can go ahead and just write, fill in I2, L, B1, mu 0 I1 over 2 pi d, and sine of 90 degrees is 1. Toward. So there you go. That's actually done, right? Because again, what we're doing and what we always do is we were given d I1 and I2, so we need to write the results in terms of d I1 and I2 and known constants. You might say, but what about L? We're asking for F per unit L. So therefore, the force per unit length of 1 on 2 is equal to I2 I1 mu 0 over 2 pi d. So that's the force per unit length of two parallel wires. And then that's attractive, or toward. Okay, sorry, we didn't finish because that's the force of 1 on 2. Now, let's go ahead. I'm just going to keep it on the same page and figure out the force of 2 on 1. Whoops. The time to really go through this slowly. Just look at it. The force of 2 on 1 is going to be I1L cross B2. I1L cross B2, which is I1L. B2 is mu naught I2 over 2 pi d. And then the right-hand rule. Okay, so what I want to show is that that was super messy. Whoops, that was super messy. But, but that's the same formula, right? We just switched the place of I1 and I2. That's the same result. But what I want to show is the direction. So even if you can't read that, that's the same result. I want to show the direction, right? So if we have I1, at I1, the magnetic field is out of the board. And by the right-hand rule, put your fingers in the direction of I1, rotate them towards B, boom, and the force is going to be perpendicular in that direction. Force of 2 on 1. So it's going to be toward the other wire. So the force is toward. So the result is F2 on 1 is I1, I2, mu 0 over 2 pi d toward. So you see that the two forces have the same magnitude and opposite direction, right? Toward for one is the opposite direction, toward for the other. So same force, same magnitude, opposite direction, as they should be, Newton's third law, or the force between two things. It's mu 0, I1, I2 over 2 pi times the separation between them. Done. But before we leave this problem, I do want to talk about signs. Let's make sure that we understand that this is a vector equation, but when we write this, this is the magnitude, and this is the direction, right? So what goes into ILB sine theta is all just positive numbers, and then we figure out the direction separately, the direction given by L cross B. So this is so again, I'm saying this without indicating what this is. So this is the magnitude and this is the direction. So positive numbers. Okay. So, but now that we figured out, and this is always the case, now that we figured out that for the two currents, this is the magnitude and that's the direction, if we reverse the direction of a current, it's like putting a minus sign in here, and then we can carry that minus sign over here, and minus towards is going to be away. If that's a little confusing to you, then ignore that, because we can just always treat ILB sine theta like a magnitude and figure out the direction by the right-hand rule. In other words, what if we reverse the direction of I2? If I reverse the direction of I2, let's say that this is that I2 is in that direction, the magnitudes are going to be the same. Nothing changes in the equations. It's the cross product that changes, right? So the cross product that changes tells me that the force on I2 is this is where we figured out the force on I2. That the force on I2, if I2 is in the other direction, then I2 cross B, in that case, you put your fingers in the direction of I2, which is now down and to the left, and then down the page and to the left, and then you cross them towards B, and the force of 1 on 2 is going to be in the other direction. So if you change the direction of I2, or one of the currents, the force is going to be, rather than toward, it's going to be away. It's going to be a repulsive force. So if the currents are in the same direction, it's an attractive magnetic force between the two wires. And if the currents are in the opposite direction of each other, then it's going to be a repulsive force between the two wires. You can figure that all out by looking at the cross product and the directions of the fields and the currents. So this is a summary of what we just said, which can be found from just applying F magnetic equals I L cross B. Oops, what did I do? Force per unit length, force per unit length. Okay. And B of a straight wire is mu naught I over 2 pi R. Direction given by, I'm just going to write RHR, direction given by the right-hand rule. Okay, so we started with these two facts, and then we figured out these two facts.